All right, now we're going to continue our discussion about the coherence of the units in Eureka Math, and I want to take you through a few examples that really show how the foundational work of a story of units, which is pre-K to 5, is really going to lay the groundwork for the 9 to 12 story of functions. So let's go ahead and get started with that. The first thing I'm going to ask you to do is multiply 15 times 13. I have here a representation of this problem. So in a story of units, remember that's pre-K to 5, the students are going to compute 15 to 13 like this. Why might I arrange it in this way, which is a rectangular array? Why might I arrange it in this way? Sure, yeah, 10 plus 5 is another representation of 15. 10 plus 3, equivalent to 13. Multiplying these numbers, like you said, are going to be easier than multiplying the double-digit numbers 15 and 13. In addition to just making it easier, which it does, it's also building a foundation for the algorithm of multiplying double-digit numbers. In addition, it's building a real intuitive understanding of how the distributive property works here. You can see it. It's very visual. 10 plus 5. We're going to do 10 times 10, 10 plus 5, just like we were distributing across, could be a binomial in algebra. We all know that the distributive property in algebra is a very difficult idea. But this is really building a foundation for that concept in a story of functions. So why don't we go ahead and fill in our partial products here. And you'll notice that this really is like an area representation, right? So 10 by 10 is 10 times 10. So help me fill this in. 10 times 10, 100. 10 times 5, this is a 5 by 10 box, that's 50. Absolutely. And a 10 by 3, that's 30. And a 5 by 10, 15. So you can really see the distribution here, breaking the partial products apart. If we were to multiply 10 plus 5 times 10 plus 3, 10 times 10, 100, 10 times 3, 30, so on. For a total sum of 195. Great. So building on this really concrete example of how to multiply double digits, let's make a connection here between this and multiplying binomials, which is a much more complex idea. But the process is the same. The foundation is in place. So I want you to look at B, part B on your handout. And notice on part B, this is labeled a tabular method. So we have an area model here. Our tabular method is going to look the same, but why might we call it tabular and not say area? Remember, we're dealing with these complex algebraic ideas. Great. So the area model is based on lengths. A length of 10, a length of 5. We can't represent a length with a negative number. We'll have negative numbers in algebra. Sure, and variables also make it difficult to represent relative lengths. Sure, absolutely. So let's go ahead and do part B. Let's fill in these partial products. I've helped you with the diagram. Do you see any similarities here? Part A and part B. Sure. All we did was replace those concrete numbers 10 with x and x, but the process here is already in place because those foundations have been set by a story of units. So let's go ahead and fill in the partial products. Help me out. X by x, so that's x by x is x squared. 5 by x, that's going to be a 5x. Right? Go on. X by 3, that's a 3x. 5 by 3, that's a 15. Look at the arrangement here. What do you notice about the diagonal diagonal terms. Yeah, exactly. We have 3x and 5x are like terms. So we can add along the diagonals. Yeah, if we had another term, if this was a trinomial, this is going to work exactly the same way. We just add a column here. And the diagonals are going to be the like terms. Great. So x squared is in a diagonal by itself, so it's just coming out x squared. It's x squared plus nothing. We got 5x plus 3x. So along their diagonal, we're going to have 5 plus 3 is 8x. And then 15, same. Nothing to add with. So 15 plus nothing is 15. And then we're just going to sum around. So the resulting product of x plus 5 and x plus 3 is the trinomial x squared plus 8x plus 15. Excellent. So again, notice that foundational concrete in a story of units, using the same process, we're able to get a little more abstract, apply this to an algebraic idea. So the next thing I'm going to ask you to do is part C. So we've started with concrete numbers. We took that process to a little more complex, a little more abstract, and then we're going to go one step further, exactly, factoring. So part C is going to ask you, using the same approach, to factor this trinomial. I'm going to give you about 60 seconds with your partner, maybe 2 minutes. Why don't you go ahead, come up with a strategy. How are we going to use this same process to do, remember, the reverse? So how are we going to use this tabular method to do the reverse? If you think back to multiplying the binomials, we were considering, we knew what was around the outside, we're figuring out the sums that come out. So out along the diagonals. If we're doing the reverse here, we're going to be thinking about the sums along the diagonals, but we don't know the partial products yet. We do know what their sums are. You got it, x squared. So this is an x squared. Along this diagonal here, we're going to have two numbers that sum up to be, 2x. And then similarly to the last problem, along this diagonal is a negative 15. So are there any partial products we can fill in right now? Right, x squared, exactly. X squared goes here, and why? Why can we put x squared? Because it is on its own diagonal. It's not summing with anything else. So we can put an x squared here. Oh, right. So that's the result of x times x, right? So there are some blanks we can fill in too. X by x is x squared, right? X by x. Anything else we can fill in? Any partial products? Sure, negative 15. Exactly, and it's for the same reason. Negative 15 is on its own diagonal. It has nothing to sum with. We got a little more trouble with these two, though, because we know they have to add to be 2x. But we don't know what they are. So take a second, tell me, or talk with your partner about a process, figure out what goes in these two blanks, or in these two partial products, and these two blanks. Walk me through it. So you thought about negative 15, okay? Negative 15 has factors 1, 15, 3, and 5. 1 and 15, can they add to be 2, 1x, 15x? No. No. What about 3 and 5? It's a negative 15, so we know one of them has to be negative. And we need a positive 2, so how can we manipulate these to make them add to be 2? Well, if this is a negative 3 plus a 5, there's our 2. So negative 3 and 5, you guessed it, are the blanks. negative 3, and 5. So our factors that multiply to be x squared plus 2x minus 15 are factors x minus 3 and x plus 5.